Saxon Algebra 2, Lesson 60. Today we just have a fairly short and sweet algebra lesson that's pretty straightforward and I hope will fit neatly into your brain. That's always my hope. Okay, there are two topics, direct variation and inverse variation. They're related, but I want to take them one at a time. Have you ever watched toddlers play? Imagine that you're in a room, like maybe a nursery at a church or somebody's playroom or something, and there's imagine open shelves and there's toys neatly organized all over the shelves. For every toddler that walks in that room, as the number increases, the number of toys that are strewn about the floor is going to increase at a much higher rate. The reason why is because each toddler does not take one toy and sit down and play with it. They take 8 or 12 or maybe 45 and they throw them all over the floor often before they sit down and actually start playing. So as more toddlers enter the room, the number of toys on the floor is going to increase with the number of toddlers, but it's going to increase at a faster rate, isn't it? Because each kid is getting out 47 toys or whatever, right? That's what we call a direct variation. Two things are varying in the same direction, right? But at a different pace, all right? We can think of lots of other examples, but I don't want to confuse the issue. John lists a bunch in the book, but I don't think that's really helpful. What we do with these is we say that one thing is varying directly with the other thing. This is the formula that we use, okay? Where K is a constant, all right? As we do the problems, this will become a little bit more obvious. In our example, we would say that the number of toys on the floor equals the number of toddlers times the number of toys that each one of them got out, let's say 47, right? That is the constant that I'm talking about. It's a special number that links the two behaviors together, all right? Let's do an example. Oh, it's 60. I was still in the 50s. 60.1. Ready? I'll read you a story. The number of boys in every classroom of a school varies directly as the number of girls. Now, there's not a lot of logic to that, but what we can do is we can write a formula. The number of boys varies directly as the number of girls. Do you see how I wrote that out in this form? I just followed the flow of the sentence. I did not overthink it, which one's greater, which one's less than. I just copied the flow of the sentence. The number of boys in every classroom of a school varies directly, that told me to use this, varies directly as the number of girls. Just let your formula follow the flow of the sentence. Do not overthink. Do not overthink, all right? It's very tempting, I understand. Now, once we get the basic formula up, we know this is going to be one of those classic two-part problems where first we'll get information, we'll solve for K, and then we'll use that to solve the second question. In one room, there are 8 boys and 2 girls. So, 8 boys, 2 girls. We'll use that, we'll solve for that, but let's get the rest of the problem. If there are 5 girls in another room, how many boys are in this room? Okay? Do not try to do something like, oh, you just multiply it by 4. It works out sometimes, but not always, all right? So work the process even when the numbers are easy. So what we want to do is we want to say 8 equals K times 2. We want to divide by 2. We get K equals 4, right? I switched the sides there. Well, that's what we thought it would be. Perfect. Glad it works out when we have easy numbers. Don't think you don't need the formula. Now we say the number of boys equals K, 4, times the number of girls, 5. So we find out that there are 20 boys. Again, our brains could have hunched their way into it, but we want to learn that process. Okay. Let's skip down and do 60.3. We're skipping over 60.2 because I'm doing both of the direct variations, and then we'll switch to the other type of variation and do that separately. The number of clowns was directly proportional to the number of performers. Okay, proportional is another way of saying direct variation. So the number of clowns was directly proportional to the number of performers. Okay, we're taking this is kind of weird. We haven't really done this much before. We're taking like a generic formula. It's like frickin' formula, kind of. Not really. We're taking a generic formula and we're substituting in the letters for our particular storyline. The number of clowns was directly proportional, which is another way of saying direct variation, to the number of performers. Clowns, performers. Just put it in that order. Don't overthink it. Did I mention don't overthink it? If there were 40 clowns, when there were 20,000 performers, wow, that's a lot of performers. That's our scenario 1. Then, how many clowns would there be if there were 12,000 performers? Okay, the numbers are bigger now. It is easily confused. Now is when we will be paid off. Does that make sense? It will pay off to use the formula version. Don't try to do it in your head. So we say 40 equals K times 20,000, simple plug-in, divide by 20,000. Now, this yields a constant that looks very weird. Let's see, 40 goes into 200 5 times, right? So K equals, ready? This is a 1 over 500. See how I simplified? I ignored those 2 zeros at the back. I compared 40 to 200. That's 5, and then this is a 1. Then I took those 2 zeros and connected them back to the 5. There's our constant. Oh, our constant can be a fraction too. All right, so that's interesting. Now we'll use this constant and this value for P to solve for C. We can also solve for this one. It doesn't have to be this one, but John's just setting it up that way. C equals K, 1 over 500, times 12,000. All right, now we just have to simplify, divide both sides by 100. 5 into 120, let's see, 5 into 100 is 20 times, and then 4 more. So the number of clowns is 24. All right. First one was easy. You could pretty much just see it in the numbers. This one was a little, I mean, this isn't rocket science, but it's a little trickier. We couldn't just look at the numbers and see them, right? If you thought that you could look at this and think, oh, it's going to be 500, not 1 over 500. So work the process and learn to use the formulas. All right, inverse variations. Now, it always kind of bothers me. There are opposites, but one is called direct variation and one is called inverse. Doesn't it seem like those words should be like direct and indirect? That just, it feels weird to me. But in these cases, remember before, as the number of toddlers rose, the number of toys rose even higher. This time, our 2 attributes are moving in opposite directions. So, for example, as the number of teenage boys increases, the number of pizza slices remaining goes down. Does that make sense? And it doesn't go down by an equal amount. 2 teenage boys can eat way more than 2 slices of pizza, right? Each boy is good for, I don't know. I would love to know, if we were sitting in person right now and you're a teenage boy, I would ask you, what's the most pizza you've ever eaten in one sitting? Because that might be our constant. If you were a girl, I would ask you how much you and your friends ate, because teenage girls can eat a lot of pizza too. We used to do a big confirmation event at my church that I was one of the leaders of, and we would order pizza for everybody to have, because we would do it around dinner time, so we would have pizza there. Teenagers can eat a lot of pizza. We ordered so much pizza, and it was always eaten. But in any case, this is an inverse variation. As one attribute is going up, the other is going down. They're moving in opposite directions. Again, not by the same amount. It's not a 1-to-1 ratio. It is an amplified effect, right? So in these, our formula is A equals K divided by B. That's how we create this kind of opposite motion, is we use a fraction. Before we multiplied, right? So let's try using this. And we just have one of these. Oh, I should write this too. The number of the slices of pizza will be the constant divided by the number of boys. Right? That's the way we would use this formula in this little story. But let's use the formula in an actual problem with numbers, because that'll be fun. Again, it's a 2-stepper. They look very much like the other problems. And we're going back and we're doing example 60.2 right now. The number, this is a little bit sciencey. Don't let it spook you. All right, I'll explain as we go. The number of revolutions per minute varies inversely as the number of teeth in the gear. All right, if you ride a bike that has gears to it, you'll know a little bit about what this is talking about. The number of little teeth, right? There's the round gear and then there's the little teeth. The more teeth, the slower you go. So if you have, it says the number of revolutions per minute. So I'm going to write RPM, revolutions per minute, varies inversely. I can set that up as the number of teeth in the gear. The more teeth you have, the slower the revolutions per minute. All right. We don't have to understand that from a physics point of view. We just need to be able to know how to take a sentence and turn it into an equation. So listen to it again. The number of revolutions per minute, don't let 3 letters freak you out. That's just one thing. The number of revolutions per minute varies inversely. Excuse me, I'm not bored, I promise. That means we need this form. It varies inversely as the number of teeth in the gear. Science doesn't matter. Oh, I didn't say that out loud, did I? Science matters, of course it matters. But in our math problem, we don't need to understand the science. Just learn to let the words flow through your ears and the math parts of them stick. If 40 teeth resulted in 100 RPM, see, it's just a number. It doesn't scare us. Then what would be the RPM if the gear had 30 teeth? Okay, this is our first scenario. This is our second scenario. We use our first scenario to solve for K. RPM 100 equals K over 40. Okay, do not overthink these. Overthinkers in the room, do you hear me? Don't overthink them. Just let the sentence flow like this. Don't try to use logic. Don't try to use science. Just let the sentence flow in the same direction and let the formula flow in the same direction as the sentence. Okay, ready? We cross multiply and we get k equals 4,000. All right. We don't know what that means. We are not interpreting anything. We are just doing math. Ready? Now we're down here. We're solving for RPM, and it equals k 4,000 over, oh, I'm using this one actually, my specific one, 30. Oh. All right. So let's figure out, I can divide both sides by 10, top and bottom. Let's do 400 divided by 3. I don't think I know that off the top of my head. Uh-oh. We've got a repeating decimal thing. So, the revolutions per minute that we will get with 30 teeth in this gear is 133.3 repeating, or you could write it as, you could change it into a fraction form. Either of these is a perfectly fine way to write this answer. John prefers this one. I guess repeating decimals are a little middle school. I guess I would lean toward that one, but I would certainly give full marks for that. And the RPM equals that. Yes, that's the right answer. All right, so what it all comes down to is, I'm going to write the formulas one more time. A direct variation is A equals a constant times B. Follow the flow of the sentence. Follow the flow of the sentence. An inverse variation is A equals K divided by B. All right, I wish those two words fit together in your pocket a little better. Direct and inverse doesn't sound quite like they're buddies, but they are. All right, there it is, lesson 60, signed, sealed, and delivered. Thank you. Goodbye.